Again, I would like to thank the organizers for this invitation and the opportunity to talk about our very recent results. I'm going to show you that part of it is published, but a significant part of it is either will probably be published soon or just under preparation. So I'm Arindam. I'm from the Indian Institute of Science, which is not very far away from here, unless you're flying. Okay, so the work that I'm going to show today is a significant collaborative effects have gone in. There are plenty of students. These three are the primary students whose work I'm going to be presenting. Manjuri and Aparna also are working in this thermoelectric business, but that work I'm not going to be showing at all. The theoretical support has come from primarily Subhro, Professor Krishnamurthy, and Manish. Calculations also, there have been other colleagues of mine, Charlie and Tanmay, who have contributed, but again, those work will probably be shown in some other point of time. Okay, so what I'm going to show today is about thermoelectricity in bilayer graphene, or graphene in general, but I'm going to show various device architecture, which eventually will lead to twisted bilayer graphene at the angles that most of us are or have been very excited about over several days over here. Okay, so if I take a very brief and quick introduction to thermoelectric phenomenon in general, it will be something like this. If you have a material and the electrons are essentially moving from hot to the cold end, and they suffer various kinds of collisions, both from static impurities and phonons, the thermoelectric phenomena can be broadly classified into two parts. One is the diffusion thermopower, and another is the phonon drag. Primarily, the static impurities will lead to diffusive behavior, and we have diffusive part of thermopower. Whereas the phonon drag is something which usually appears at slightly higher temperature, where you've got a large number of phonons, which drag the electrons away as through this, and leading to very strong and fast increase in thermopower as a function of temperature. If you see gallium arsenide and aluminum gallium arsenide kind of a semiconductor structure, the electron and phonon couplings are so strong that the phonon drag effect usually dominates over the diffusion thermopower at most measurable temperatures above a Kelvin or a few hundred millikelvins and so forth. Okay. However, if you take the diffusion part of the thermopower, which is, any standard textbooks will give you a very nice semi-classical Boltzmann transport description. You have electrons moving from one end to the other. The total current is essentially determined by the change by the gradient of temperature and the electric field, and which leads to, which can be connected together, leading to one of the celebrated expression of thermopower in condensed matter physics, which is called the Mott thermopower or Mott formula. The basic idea here is that you have the thermopower or the Seebeck coefficient S, which is proportional to the derivative of the conductance or density of states, primarily conductance in this case, which can be split into two parts. One part is essentially the part where conductance changes with a function of density, and then you multiply that with the density of states of the system, which is under study. Okay? What's important here to realize is this part is directly measurable through experiments, and this one will be determined by the specific system that you are looking for or looking into. Okay. As far as graphene is concerned, thermopower has been a fairly well-studied quantity. This is the data that came nearly 10 years ago from Philip Kim's group. And what's important here to realize is that you have this graphene, and the thermopower is essentially linear. This is conductivity. Even thermopower is linear with temperature over entire temperature range from low temperature to room temperature. That's because in graphene, the electron-phonon coupling is extremely weak, and hence the phonon drag phenomena is usually significantly lower than the diffusion contribution to the thermopower. Okay. This is something which Aditya did in our lab. Essentially, you can see how nicely graphene this is a bilayer graphene data, can agree to the Mott semi-classical description. This is the resistance as a function of gate voltage, and then this is the measure thermopower across the system. And this is the measurement. And if you simply take this derivative from the experiment and use the density of states of bilayer graphene, which is standard parabolic one, you get an extremely nice agreement with the semi-classical description. Very good. So we know what we are measuring. So that then comes, okay, what happens in twisted bilayer graphene? I'm certainly not going to give you any introduction or in detailed information about twisted bilayer graphene. Everybody knows here. What's important here is to realize that when you make twisted bilayer graphene, it is not just the electronic hybridization that takes place. Along with electronic hybridization, you also have vibrationalized hybridization between two layers. For example, what's unique about this is that you have a new phonon band develop, which is because of the hybridization between the out-of-plane vibrations or the breathing modes. And that leads to this additional branch called the ZO phonons. Usually these are fairly low energy optical bands, and you can see from the Raman spectroscopy, they come out around 100, 120. There are shear modes as well, which are even lower in energy. So there are these two effects, but the electronic hybridization and phononic hybridizations are usually simultaneous in twisted bilayer graphene. So the question that we ask here is that, okay, can thermopower cast a light on both electronic and vibrational states in twisted bilayer graphene? I'm going to talk about first the general framework of the experiment that we have done. This is not a standard current voltage characteristic measurement, but it requires certain engineering of the devices themselves. So the way we can do these experiments is we take a graphene and what we do is that we either can heat it using an external heater, and that sets up a temperature difference across the system, and then you can measure the voltage, which are called the thermal voltage or Seebeck coefficient, Seebeck voltage, whatever it is. Alternatively, you can heat, and this is what we generally follow in our experiment, in our laboratories, that you heat the graphene itself at one end, and that sets up the thermal gradient across the system. You can do the same thing for twisted bilayer graphene when you make them. And this is a typical twisted bilayer graphene. But here what we do, and I'm going to explain to you why, we make our life a little more difficult for ourselves. We try to make it, give it turn an additional 60 degrees, in addition to the kind of angle that we want to do the experiment at. So the reason being here that we can access both layers independently when we want to, okay? So that means now, since I have this overlap region, which is about 60 plus the theta that we want, we can have the electrodes on both graphene independently. As a result, we can measure the thermoelectric power both in plane and cross plane. It means that, for example, in this case, we pass a current on this, so we heat up the upper graphene with respect to the lower, and we measure the voltage between this point and this point, which gives us the cross-plane thermal or Seebeck coefficient. Alternatively, you can actually heat up here and then measure between this point and this point, which means this region can now be probed. The thermal voltage that is generated in this region reflects in the measurement. Okay, so these are two different measurement schemes that we have followed. I'm going to first show you the kind of measurements, the result that we get here. But once we get strong hybridization between the upper and lower layer, particularly at low angles, we'll see that this particular orientation doesn't really make any difference. Whether you measure cross-plane or in-plane, they're all the same. Okay, for experimentalists here, very few, I know, but still, there's the way we make the experiments is we take silicon oxide surface, we put a boron nitride layer, then we put a layer of graphene, we put a second layer of graphene at an angle that you wish to, and then we put another layer of boron nitride to cover the overlap region where you form the twisted part, and then we put another gate to cover the overlap region. Now, important experiment here is that most of our experiment are done by varying the gate voltage of this particular gate because it only affects the overlap region, whereas the lower bottom gate is usually used to apply a large gate bias to make the rest of the stack or the cross pattern reduce the contribution from these regions substantially by doping them to a very high value. This is a typical experimental device, but there are plenty of devices although this is the general structure. Okay, very quickly, this is the part which Subhro covered in the first day of the meeting, so I'm not going to spend too much of time on this. What happens at large twist angles, particularly when the two layers are decoupled for most practical purposes? Here, what we do, we pass a current to the upper graphene, heat it up, and then measure the voltage between upper and lower layers. If you take the standard electrical transport, you see the R cross plane, as you dope the graphene using the top gate, it comes down like the standard graphene, and you get the it's a standard bell-shaped curve. If I measure the thermoelectric power now, the thermoelectric power is measured by now heating the top graphene and measuring the voltage between upper and lower layer. You get exactly what naively would expect from the differentiation of the conductance. You can see that over here the thermal voltage is positive because it's electrons. On this side is holes, and this side is electrons, and it's negative. Okay, so as you change the heating current, you can see the thermal voltage is increasing, and if you normalize it by I square, you can see beautiful collapse, which means essentially that we are looking at the thermal voltage and not some extraneous contribution from somewhere else. Yeah.
One of the things about generating current using heat current using electricity is you get nonlinear. If the contact is non-ohmic even to a small fraction, you get higher harmonics without doing anything.
Correct.
Without invoking thermal physics.
That's right.
How does one take that into account?
That's an excellent question. Actually, one of the, we have seen exactly that. You go to higher harmonics and you divide it by that power of current and you will end up getting a collapse. Yeah, true. So most of it, I would say, we look at the other features of thermoelectrics. We see the Mott formula, we see the whether they agree or not, and also try to keep the heating geometry as well defined as possible. There's one unique aspect here is that we always use graphene as the contact rather than metal directly as the contact, where the contact effect can probably be significantly reduced. But we have seen this effect, and we are aware of it at least. Okay, so if you see the Mott formula, if I take the derivative from here, you can see this is the experimental, the blue ones is the experimental geometry, experimental curve, whereas if I say the derivative from the Mott relation, it doesn't match at all. So it's a apparent violation of Mott formula. And if I take the temperature dependence of thermopower across from low temperature to room temperature, you can see rather than being linear here, it's actually saturates. Now it turns out that this saturation can be quite nicely fitted with the derivative of the Bose-Einstein of the occupation number, which gave us the idea possibly this is a phonon drag effect in which your hot layer is a larger number of phonons which kicks the electron out of the layers, setting up a voltage difference between the two layers. And as a result, you have a thermopower which is fairly well described by this expression, and it also allows you to know what the phonon energy that are responsible for this kind of a behavior. It turns out that this agrees wonderfully with the zone boundary phonons in the layer breathing mode. Right. So this part is more or less under control now. Essentially, we have a Coulomb drag at the individual van der Waals junction when the two layers are completely decoupled at an angle of 12 degrees or so. What happens if you go now start making the angle smaller? So what I'm going to show is that I'm going to take you 13 degrees, they're about 0 degree, where by accident when the students created the layers, the bilayer, it became a Bernal stacked system. So that's 0 degrees as such. Normally, they're determined by Raman spectroscopy, although it's not a great detector or not a good way, but at least we can go ahead and show you what happens. This should appear very soon in print. Okay. Typically, the electronics conductance as a function of temperature and gate voltage. So this is the experimental geometry. We have two layers, and we send the current from one layer to the other. You can see if the angle is large, you have a very different behavior than when the angle is small. This is 12 degrees, this is 2 degrees. This is not magic angle yet. It is significantly far away from the magic angle, but the nature of temperature dependence changes dramatically, okay? And this is something which we see in most low angle samples, which is a very weak temperature dependence over a pretty wide range of temperature. These are close to, I mean, it goes to from charge neutrality point. This is charge neutrality point. This is heavily doped region. Okay. So what happens with thermoelectric power? Again, now very different from the completely high angle thermoelectricity. Here we see a very different behavior. This is at 2 degrees. And again, now what we do is we send the current on the upper layer and measure the voltage between upper and lower layer. You see that this one is the experimental data, and this is the Mott expectation. And you can now see that the Mott expectation is significantly well, it describes data quite reasonably over most temperature. And more importantly, we now recover the linear temperature dependence that is expected out of Mott relation. So what if I now categorize, and this is very interesting, we now have got 7 or 8 different angles. You can see that at angle larger than around 5 degrees or so, the Mott, the thermopower as a function of temperature is completely different from angle slightly less than 5 degrees, which is very linear for over the entire temperature range. Over here, it's saturating, okay? Excuse me. Right. Current understanding is based on coherence of electronic wave functions between the upper and lower layers. Again, a calculation by Alan McDonald about 9 years ago. You can say the RC time constant of electronic transport across the 2 layers. If I take the phonon frequency, which is roughly here, over here, then at this region, which is lower angle of lower than about 5-6 degrees, it's the coherence of the wave function that is more effective to take the electrons from one layer to the other, whereas when the when the angle is larger, it is the phonons which is more effective to take the electron from one side to the other. So that's reasonably matches the experimental observation. There are a couple of very important points. It's extremely sensitive to band dispersion, and this is very interesting. You see, this is the data that we took at 150 degrees for a bilayer graphene. This is the bilayer graphene. And what we did, we tried to fit the Mott expression with single layer density of states and bilayer density of states. There's clear difference between the two descriptions. So it means that the thermopower measurement is extremely sensitive if you want to look at the density of states at low energy features. And this is exactly what Adhip has seen. Recently, what happens is in case of a bilayer graphene, it is this, gamma 3, the skew interlayer hopping, essentially the interactions between the next to neighbors, and that leads to a trigonalization of the density of states at low energy. So that leads to usually a kink over here. And normally in the resistance versus gate voltage characteristics, you see the red one, absolutely you can't make out anything at all. The moment you do thermopower measurement, you can see that additional kink here, which cannot be explained if you simply take the bilayer graphene wave function. But what Aditya did, he calculated the density of states, including the trigonal warping, and you can see this additional feature now gets reflected in what thermopower is giving us. This is low temperature, it's about 0.3 Kelvin. I think I have to cross-check with him once. Okay, now what happens? Close to magic angle. Now it turns out over the last few days, I have to say that getting magic angle is far easier in theory than in experiment. And this is something which, I don't know whether Abhay agrees or not, but his... Right. So we have been working towards it for a very long time with plenty of different structures. Turns out that we have been getting closer, but we are not at 1.08 or 1.1. So I'm going to show you the data on a device which is at 1.4 degrees, which comes out by looking at the various transport and characteristics in Raman spectroscopy and so on and so forth. So this is a typical device which has got about 1.4 degrees angle. we should be posting it. I told them to post it in the next week or so. Please make sure that it happens. I've told it in front of the entire hall, so you have to do it. Okay. Right. So this is a typical structure. This is approximately 2 micron by 2 micron area. The way this experiment was done is that we heated up one of the graphene layer and hence set the temperature across like this, measure the voltage in these 2 leads, which leads to, in the real device, we measure between this point and heat up these two leads, through these 2 leads and set the temperature difference. Okay, first, why we do this? Sorry, the thermoelectricity is a very interesting and important probe for strong correlation. The sodium cobaltate is extremely well known, where the thermal power that you get is 100 times larger than what would one expect from some simple Mott expectation. But what we are going to do today is probably best described by this early work from the Würzburg group, which came from, condo-coupled quantum dots. I'm going to just use it as an example so that I can tune you for what's to come. So this is a quantum dot, and these are Coulomb blockade oscillations. When the quantum dot has got an odd number of electrons, you can see the conductance is significantly larger, and this is by now more or less understood as because the virtual coupling between electrons and the localized spins of the quantum dot, and leading to a two-body correlated state at these points. Now, what you see here is that if you take standard differentiation of the quantum dot conductance as a function of energy or the gate voltage, then you should get something like this, where every time that there is a peak or a minimum, the thermal power must cross 0. It doesn't happen when you are here and here, where there is a condo correlation that has been set in. You can see the thermal power, the measured thermal power, does not cross 0, even though the expected Mott value crosses 0. Okay? So that means that there are those points where you have additional contribution to thermal power coming in, which in this particular case they assign to some form of a spin entropy that goes from one side of one lead to the other. But one can look into more detail of that. But this is the most important aspect, that when you have got correlation in present, the Mott formula is violated in certain ways. Okay. This is our experiment. Now we are back. So we have this, now we have this 1.4 degree angle. You can see this is the primary Dirac point, and these are the secondary Dirac points that come up. You apply a magnetic field, and then from there we can get roughly, these are, from the Landau fans, we get angles of about 1.4 degrees. So that's another way, or more reliable way, I would say, to measure the angle. This is the temperature dependence of this system. You can see that this is a temperature dependence that goes all the way from 3 degrees to 240 degrees. At low temperature, it's nice and sharp, but then at very high temperature, sort of develops into a shoulder rather than anything else. That reflects in the temperature dependence. I'm going to show the very unique temperature dependence of this system. So, for example, if I take different densities, this is the main Dirac point, the 2 secondary. If I look at 4 orders of magnitude of temperature dependence, it's weakly metallic, I would say, but at the Dirac point, the main Dirac point, there's always a problem of inhomogeneity. So specifically saying about what should be the temperature dependence is not very universal, I would say. So we wanted to go at specific points. I'm going to show you the temperature dependence at this point, which is at the complete NS. By the way, I will take the same definition of NS as what Rajdeep did. That is, it is the density at which the Moire band is completely filled, which is this one. You can see this is a unique, weird behavior. This is at this point. At high temperature, there is an insulating behavior which becomes a metal and remains a metal all the way down, in spite of the fact that there is supposed to be a pure band gap should appear in the system. And exactly the same behavior that you see on the other side, which is on this side, where again, the system shows an insulating behavior at temperatures approximately 100 degree and above, whereas the system becomes a metallic behavior with no, and this is not about Bloch-Gruneisen problem because we go all the way down to 10 millikelvin, it remains metallic all the way down to few millikelvin temperature, okay? What happens at half filling? At half filling, this is at 3 degrees, this is at 1.4, so we don't see a clear peak in the half filling regime, although there are some thermal cycles at which we observed tiny blips coming here which can be easily destroyed by magnetic field. But in this particular case, at least, we do not see any peak at half filling. However, even at half filling, you can see the system is extremely metallic all the way down to a few millikelvin temperature, and this is exactly the same case where on the other side of the story, okay? I've got 5 more minutes, so I'm going to now go very quickly through the thermopower data that we have got. Okay. Yeah. Right, this is the thermopower behavior now. This is again the resistance, and we have got the secondary peaks at high temperature, which is 60 degrees or so for us. You can see Mott formula is by and large okay, because where you are at peak, it's kind of trying to go, it didn't go, but so this part I don't understand much. But let's concentrate on half fillings on this side and this side. You can see that thermopower is 0 roughly where the half filling takes place, expected from Mott expectation, okay? Where the flatness comes. Okay, I'm cooling it down now. I'm going to go from 35 Kelvin, and now you see that in addition at the half filling, there's a tiny blips that's developing. You go to farther lower temperature, 20 Kelvin, again, these peaks are getting stronger. This is significantly strong peak, complete violation. Here you can see that this is flat. Thermopower, according to Mott formula, must be 0, but we are seeing a peak over on this side and a trough, a minimum on this side. You can see go farther, 10 Kelvin, the peaks are completely developed. Thermopower, Mott formula is entirely violated. There is no evidence that you can explain this from a single particle physics anymore. 3 Kelvin as is kind of continues to the lowest temperature that we can do these measurements at. We took this data from Shinjun and Manish and converted to the density of states and looked at what the Mott formula would give us. I don't want to put too much of importance at this region, but you can see what's important here to realize is that in spite of the fact that the twisted bilayer at 1.4 can have a complex density of states, if I am to obey the Mott formula, the density, the contribution to thermopower at these points must necessarily be 0, like this pink region. This is the expectation from Mott formula. You can see this part must necessarily be 0, but we are getting a significantly large deviation from these points. Okay, so these are the excess thermopower that we are quite excited by. Couple of slides, magnetic field. So we did this experiment now in magnetic field. In parallel magnetic field, there is absolutely no effect, or at least nothing that of significant in nature that I would be very excited by. So you can see at 9 Tesla or so, there is a slight marginal decrease, although I'm not sure whether this is because of the way we normalize the data that has caused this. But overall, parallel magnetic field doesn't seem to be affecting this violation of Mott formula in our devices. I'm more or less done, so this is the conclusion that thermoelectricity across twisted bilayer graphene at last twist angle is determined by the coupling of electrons and interlayer breathing modes. The Mott formula is recovered at low angles because you have got the coherence set in, and this diffusion thermopower is probably, or rather than the coherent transfer of electrons from one layer to the other determines the thermoelectricity. You have got thermoelectricity is sensitive, you can clearly see, and the new anomalous contribution at half filling close to the magic angle. Thank you for your attention. Yeah.
I'm not sure I understand the philosophy of analyzing the data. Yeah. In the first part, you showed deviations from Mott law, and then you attributed them to phonons.
Yeah.
And actually, it would be interesting to see the temperature dependence, just to confirm that these are indeed phonons, which you have not shown, or do you have this data?
I'm sorry, are you talking about the first part?
The first part.
Yeah, the first part, we have the data. So the temperature dependence is entirely governed by the occupation number of phonons. And as a result, it is the temperature dependence of thermopower is directly proportional to the derivative of the Bose-Einstein distribution. And from there, we can extract the energy of the phonons, and that agrees to the breathing modes in twisted bilayer graphene.
Okay, so and in the second part, when you see deviations from Mott law, then you say that you attribute this to the fact that the density of states is not what is calculated, or what.
Okay.
I mean, you have a different reason for.
Yes, absolutely. Sorry, let me clarify this. So what we find is above 5, when the twist angle is larger than 5 degrees, the two layers are essentially decoupled, and entire physics of thermopower is determined by the electron-phonon interaction. The moment you go below 5 Kelvin, and which includes the last sample, which is at 1.4 degrees, it is the electronic thermopower that dominates the entire show, and there the phonons play no role, certainly at low temperature. There we've recovered the Mott formula when the two layers are completely decoupled still at 2 degrees, for example. The two layers are not hybridized, but the thermopower is determined by the electrons. What happens close to the magic angle, which is 1.4, the Mott formula is again violated, but now the reason for violation of Mott is because of strong correlation, we believe, than the phonon parts which violated the Mott formula in an earlier case.
So one question, maybe just a question of nomenclature. You said something about coherence of electronic wave functions. Did you just mean that the hopping is large enough that...
That's right.
Okay.
That's what I mean.
Then the other thing was, I didn't get why at half filling for 1.4 degrees, one should expect the thermopower to be 0.
Oh, no, it's not a thermopower, it's a Mott formula. So for example, at half fill, if you take this resistance versus temperature versus density dependence, you have a minimum here. So if I take the Mott formula, dg dn must be 0.
Okay, so you're saying from experiment, that's nothing from theory.
Well, I mean from Mott expectation.
Okay.
Yeah.
Okay.
Yeah, sorry. So this is expected Mott behavior.
Yes.
Yeah.
The insensitivity of the excess thermopower to parallel magnetic field.
Right, right.
Do you have any comment on the role of spin?
Well, I can comment there is, if this had been because of spin, then it should have been affected by the in-plane magnetic field, which is, and also the fact that the excess thermopower starts coming in at significantly larger temperature than what the standard Mott physics in twisted bilayer graphene is, also tells me probably this is not connected to spin. Okay, so what exactly is that is something that we have to figure out. Yeah.
So as you said that the 5-degree angle is somehow some cutoff, means below which the Mott formula is valid.
Right, right.
Now if that the Mott formula is not valid. So is there any physical quantity or which says that this 5 degrees somehow the...
No, unfortunately, at least we do not know of any, this is where exactly the hopping, what you said, the hopping rate becomes significantly large between one layer to the other and exceeds the phonon frequency. Okay. And as a result, it is the electronic thermopower that dominates rather than the phonon-driven thermopower. Yeah.
Okay, if there is no questions, so let's thank Arindam once again.
Thank you.